Hello everyone, welcome to Illustraca. So this is the first lecture of our new series on a very fundamental subject of civil engineering or any engineering, core engineering, which is strength of materials or mechanics of materials. So this subject is a very fundamental subject and very important subject also. And this series I'm making specially for the diploma and undergrad civil engineering students and the professionals, those who are willing to brush up the things again. Obviously it is known to everyone, so those who want to brush up then can also see it, and I hope it will be helpful. So let's begin. So today's first topic that I have taken is Hooke's law and stress strain. So before getting into Hooke's law and stress strain, we will understand few more things. So let's begin the session. Suppose I have taken one bar. Now this bar can be of any material. Okay, it can be of wood, it can be of steel, it can be of concrete, any materials. Okay, I'm not considering any I can say particular material in this bar. I'm considering this is a bar, it's a prismatically it is a prismatic bar and of any material, and I am applying a force to the end of this bar like this. In both ends I'm applying some force F, suppose F1. So now as I applied two forces, what will happen? The bars have some molecules or particles, right, like this inside it, though it will not be visible like this, just to represent or just to make you understand this. So it has something like this, and they also have some force acting in between them. These molecules also have some force in acting in between them. So when I have applied a force F1 on this particular area of the bar, so what will happen? These molecules of the bar will start moving like this. Correct? These molecules of the bar will start moving. So if this particular molecule is coming here, okay, so all these molecules will be coming like this. So you can see we will see some deformation in the bar. That means, okay, we may see some deformation in the bar due to the displacement of the molecule. So if I just zoom this area, suppose this is my bar and it is subjected to some force in this direction. It had some molecules like this, suppose. Okay, it had some molecules like this, molecules or particles. Due to this applied force, so what will happen? These molecules will start displacing. Okay, these molecules will start displacing like this. So in that case, due to the displacement of the internal molecule, so what will happen? We will see some deformation. Okay, so here you can see this is the deformation that we have seen. Sorry, this is the deformation that we can observe. Okay, or we may not be observed by open eye, but this kind of phenomena may happen, and this is because these molecules are displacing actually from this point to that point. Correct? So the same thing happening at this end also, and as the force is acting, suppose this is the axis of this particular bar, and if I apply the force exactly along the axis of the bar, total bar, what will happen? All the molecules present in this you can say bar will equally displace. So obviously from the center, suppose center of this bar, some molecules will displace in along this direction, some molecules will displace along this direction. Correct? Fine. So when the molecules are displacing, and we can see a deformation which is elongating the bar. Okay, it is elongating the bar. The length of the bar is increasing. So in that case, so we can say this is elongation. This is elongation. Okay. So in this case, this force that we have applied will be called as tensile force. Okay, this force that we have applied will be called as tensile force, and this bar, we can say, is subjected to tension. There can be many other cases of tension, but I'm just explaining in this way. Okay, there can be many other cases, tension due to bending and all these things we will see later, but now this is the very fundamental that we have started. Now the similar way, I hope it is clear. The force that we have applied, which is you can say displacing the you can say molecules, and due to the displacement we can see some elongation of the in the length of the bar. So in both direction, obviously, as we have applied in both direction force, if it is applied in one direction, so elongation will be only in one direction, correct? So this, due to this elongation, due to the force, this elongation occurred. So this force we will call it as tensile force or tension. We can also call it as tension, and we can also say this bar is subjected to tension, correct? Now if I take the same bar, yeah, and if I apply now force like this, and I'm assuming this force also along the axis of this bar. Okay, so now what will happen? If I again zoom it like this, this is my bar. Okay, I had molecules like this, or the particles like this, particles of the material of this bar. Okay, so particles like this, and this is subjected to some force which is along the direction of the bar, or along the direction of the obviously along the axial axis, but it is not going you can say away from the bar, but it is towards the bar. So what will happen now this particles will move in this direction. So obviously, as these are moving in this direction, there is no, I can say, unlimited space. There will be some restriction. But other particles also are there. So what will happen? The particles will start coming closer. So here also we will see displacement, okay, of the particles, but these particles have started coming closer to each other. Okay, so in this case, as the particles started coming closer to each other, again we will see some deformation in the bar, and this is the deformation that we have seen. This is the deformation that we have seen. Okay, so what we can see, this is reversely elongating. That means it is not increasing in length, it is decreasing in length. Okay, so I can say decrease in length. Okay, when this kind of phenomena is occurring, then this force which is applied on the bar is called as compression, or you can say compressive force, or I can say compression. And we can also say that this bar is subjected to compression. Okay, fine. So we understood what is tension and what is compression. Okay, very basic idea I have given. Now suppose I have taken a bar and somehow I fixed it here. Okay, here I have fixed it. It will not move. This edge will not move. Now what I have done, I have applied some force downwards. So as this force is going towards, or you can say opposite to the direction of the bar, face of the bar, so obviously it is a tensile kind of force, we all know. And I'm assuming that this force is along the axis of this bar. Okay, there is no other deviation, it is totally exactly along the axis of the bar. So now what will happen? Obviously, as we have seen earlier, the molecules will displace, the particles will displace, and we may see some elongation in the bar. So if I just draw in a different color, maybe green, yeah, so we will see some elongation in the bar. Okay, so this is the elongation. Suppose we are denoting it as small delta. Okay, this displacement or elongation, we are denoting it as a small delta, or let me write it as P now. Okay, so I have applied a load P, force P along the axis of the bar, and the elongation we are seeing, it is the small delta. Now if we take any section on this total bar, suppose the length of the bar is, this length of the bar is suppose L, and if I take any length DL, okay, suppose this is DL, here also the elongation that we will see, it will be equal to the D small delta, correct? Correct, because this elongation will be equal at so I can say this elongation will be same in any section of the bar. Okay, that means it will be uniform at any point of this particular bar, as we are considering that the load is totally acting along the direction of the axis, there is no deviation. Okay, so it will be uniformly elongating at any section, correct? So this is not required actually. Now we will come to this point later. Fine, so this is my L total length, and this elongation I have considered as you can say small delta. Fine, so I have applied a load and it has elongated. So due to this elongation, this body, this I can say bar of any material that we are considering, obviously it is a body, correct? So this body has done some work. So if I say, while elongating, this body has done some work, right? As per the definition of work, it has changed its point. Every single point you can say on this particular bar has displaced along this direction. Okay, and we have some linear displacement also. Fine, so it has done some work. So this work will, I will write it in a this way: work done by the body. Okay, so it has elongated, so that means this body has done some work. So this work will be transformed to this work will be transformed to a potential will be transformed to a potential energy in this bar. Okay, this particular you can say work that the body has done while elongating. So this work, obviously it has done some work, so this work will be transformed to potential energy in this particular bar. Correct? Fine. So this is the same thing in case of spring also. I think we have studied in the 11-12 physics that we have a spring. If we just elongate with this with a load P or force P, so what will happen? We will see some elongation like this. Sorry. We will see some elongation like this. And due to this elongation, some potential energy will be stored in this spring. Correct? Similarly, in this bar also, some potential energy will be stored, or you can say transformed due to the work done by the bar or by the body. Fine. Now if this load, if you remove the load that we have applied, okay, if I remove this load, what will happen? So obviously the molecules between in this bar, they also have a you can say forces acting in between them. So as we have applied the load, so the molecules have displaced and we have seen the elongation. Now if we remove the load, what will happen? These molecules are, you can say, will provide this what I should say, a reverse deformation. Correct? So I am applying force here. It is I can say deforming along the downward direction. I am removing the force. So what will happen? This due to the forces acting between the internal forces acting between the molecules, we will see some you can say reverse deformation. So I would write it here: due to unloading, we will see uh, I will write it here, reverse deformation. Okay, we will see a reverse deformation. Correct? So this reverse deformation, why it is happening actually? Why it is happening? Because this potential energy that is being stored due to the elongation of the you can say body due to the work done, after unloading, this potential energy will again transform to a reverse force. Okay, why this reverse deformation will be happening? Because the stored potential energy okay, will be transformed to a reverse force, which will let the molecules to go back to their previous position, okay, in the initial position. So now if the body, or you can say if the bar or molecules of the bar, or I would say particles of the bar, molecules of the bar achieves sorry, I will come to this point later, a bit later. So now what I will say, this reverse deformation after unloading. Okay, so what we have done, let us see the phenomena totally. Unloading, then this potential energy, or I will say transformation of potential energy, transformation of potential energy, P, I have written. Okay, it will create a reverse deformation, reverse deformation. Okay, so due to the reverse deformation, the molecules of the bar will get back to the previous position, get back to their initial position, initial position. Okay, I have unloaded, I have removed the load, all the, so this potential energy converted to a reverse force, and this particular you can say the elongation that happened, it will reverse and it will come to this point again, right? So this phenomena, this total phenomena is known as, this total phenomena is known as elasticity. This total phenomena is known as elasticity. Now if the bar is capable of, if the bar is capable of achieving its initial condition after the unloading of after the unloading completely, okay, then we can say this is the what I should say, this is the ideal elastic object or material. Okay, so I would say, I will write it here. If the bar regains its complete initial position, complete initial condition or initial condition, okay, then the property of the material which helps it, I would write the property of the material of the bar, okay, property of the material of the bar that helps, that helps it to regain its initial position, regain its initial position, is called as elasticity. Okay, and the material is purely elastic, purely elastic. Okay, understood? So what I have seen, that I removed the load, it was the bar, it has deformed like this, it was loaded. Now if I remove it, if I remove it, it will go back and it will get back its position again, regain its previous position, initial position. So it is completely elastic material. Okay, it's a purely elastic material. Okay, the whatever material we have used to make this bar, it is a purely elastic material. Now if any cases, suppose this is my bar, it has elongated up to here due to the load, and after removing, if it is not regaining its initial position, suppose it has gone up to here only, so here it has not gone to its complete initial condition, then we can say it is a partially elastic material. It is a partially elastic material. Okay, because it has not achieved its exact initial position after the unloading. Okay, so now you will see that you will say that I have removed the load. So if I want to create a equilibrium, if it should be equal, right, I have removed the load, so it should achieve its exact actual position. Then how it has not achieved this exact position, then how you can balance? So basically, in case of partially elastic materials, when you will be loading it, it will be, you can say, creating transforming the potential energy, transforming the work done to potential energy. And when you will be unloading it, it will not achieve its exact position, because while deformation, okay, it has also generated, due to the work done, some heat or some other energy has also generated, which is dissipated, which is okay. It has, suppose this is my bar, and elongation happened due to the load of P. So not only elongation happened, along with this some energy deformation also happened. Sorry, energy dissipation also happened. So I will write energy dissipation, DSCIPATION, I guess, PITION, something like that. Okay, so here we got delta plus energy dissipation, which is equal to this P. Correct? So when you are, this energy already dissipated, correct, so you cannot gain energy again. If you remove this P, the energy it is not gaining. So obviously, as the energy is not gaining, if I remove this particular part, okay, so you cannot make it equal, because this P is equal to combination of these two. Correct, combination of these two. So obviously, if you want to make it P and delta equal, in this case you need to minus some value. So suppose some delta 1, so it will come, suppose, up to here, and this is my delta 1. So now it is balanced. So this delta 1, you can say it is equal to the energy dissipation. Okay, I cannot say how much it is, so I am just saying that it should be equal. So you have to balance it somehow. So if you want to balance, so whatever energy is dissipated, that amount, due to that energy, whatever I can say elongation has happened, okay, elongation would be happening, that elongation, that much length it will not regain. Okay, so when this energy dissipation condition will come, okay, so this condition or this behavior, we will say, we will call it as, this whole thing we will call it as inelastic behavior. Inelastic behavior, that means it is not elastic. Elastic means it is regain its actual condition, but here it is not regain its actual position or initial position, so it is an inelastic behavior. Okay, in elastic, completely elastic behavior, there will be no energy dissipation, there will be change of length, and after unloading it will regain its actual length. Fine. As the energy dissipated, so to balance, some length will not be, cannot be achieved. I'm just you can say explaining in a different way, not totally in the you can say things which are written in the book. So if you read, you may get more detail in there. So I'm just saying, to balance it, some length will not be regained. Okay, so that means it is an inelastic behavior. Okay, so whenever after loading, if we see that some energy is dissipating, that means we can say that that material is going beyond its elastic limit. Okay, it is going beyond its elastic limit. It has reached its elastic limit. Now it is not capable. That means the point after which the material or I will say the body cannot regain its initial position uh, after unloading. So that point is called the elastic limit of the material. Elastic limit of the material of the body. Okay, at a point, after reaching this point, it will not regain its initial position. Okay, due to the constant loading. So I hope it is clear what is elasticity, what is inelastic behavior. Okay, what is elastic limit. Fine. So what the what is being you can say observed, that due to the applied force, some elongation is happening. If it is up to its elastic limit, then it will regain its position. If not, it will not regain its actual position. It will dissipate some energy and it will partially regain its position. Correct. So applied force, okay, is equal to, or you can say proportional to, I would say the applied force that we can say P is somehow proportional to the elongation that is happening in the bar. Okay, if you increase the, obviously if you increase the load P or force P, what will happen? The elongation will increase. Obviously if it is beyond its elastic limit, it will not regain its position. If it is up to its elastic limit of the material, then it will regain its position. But it is linearly increasing. You increase 1 unit, here also elongation will increase 1 unit. You increase 2 unit, elongation also increase 2 unit, like this. Okay, so this particular thing, sorry, I'm not getting the eraser. Okay, so this particular experiment is being done in different materials, and the similar kind of behavior is observed in 1678. In 1678, an English scientist whose name was Robert Hooke. So Robert Hooke has observed with different materials due to the by doing different you can say the same experiment, that the applied force is proportional to the elongation that we are seeing. Okay, if you increase the applied force, the elongation will be increasing linearly. So this simple linear equation first observed by the English scientist Robert Hooke in 1678. Okay, and he has come up with one equation for this linear a behavior, which is the elongation delta equal to small delta equal to P into L. P is nothing but the applied force. L is nothing but the total length of the bar divided by A into E. Okay, so what is this A? A is nothing but the cross-sectional area of the bar, and E is nothing but the modulus of elasticity. I will come to this particular point also. So I will just write it here. P is the force, L is length, actual length. Okay, A is cross-sectional area, cross-sectional area, and E is modulus of elasticity, or Young's modulus. Also, it is also called as Young's modulus. I will write it as modulus of elasticity. Elasticity. So now we can easily understand the condition that if we increase the load, the elongation will be increasing. If we increase the modulus of elasticity of the material, then deformation will be decreasing. Okay, the more the modulus of elasticity, the less the deformation due to the same equal applied force. Correct. Now here, this, if you see, this delta is also inversely proportional to the area of the bar, cross-sectional area of the bar. So suppose this is my bar. If I draw a cross-sectional area, so it will be something like this. Suppose this is my A, this A into B, so A equal to A into B. This is my cross-sectional area, right? So it is saying that the cross-sectional area is inversely proportional to the elongation. That means, want to say, if this is fixed, this is my bar, and I have applied some load P. So with increase in length, what will happen? With increase in length, we can see this cross-sectional area also reducing. You have seen, obviously, if you take a rubber band, you try to elongate it, you will see the thickness that the rubber band had in the initial condition. When you are stretching it, the thickness is reducing in between. Correct? So this is what Hooke also observed, and he has given this overall, you can say, equation, linear equation for this particular condition. One is delta is proportional to the applied force P. Delta is reversely proportional or inversely proportional to the cross-sectional area of the bar or of the object, and also it is reversely proportional or inversely proportional to the modulus of elasticity. Correct? Now if I take the bar, again we will discuss this with bar only. Okay, so I have taken the, suppose this is my bar. Okay, I have fixed it somehow. This area is fixed, it is, and I have applied some load P. Now if I make a cross-sectional plane here, okay, if I just cut this bar here, and if I see it here, so this is my section, this is the axis of the bar, and I suppose I'm assuming that this load is acting exactly along the axis of the bar, as I have already said. So what I will see that, or what is being observed, that when the load is exactly acting along the you can say axis of the bar, if it is a point load, you need point load. So in this case, point load means it is acting at a particular point. Okay, so in this case it can be a uniform force also, so you can apply like this at the whole area. Okay, you can apply like this also, but we have not done it. We have applied a point load only, point force only. So now what is observed, that when you are applying it along the exactly along the axis of the object, so we will see this particular, in this cross section, we will see there is a reverse force, obviously, action and its reaction. So what it will do, the molecules of this object, it will try to I can say try not to elongate, and obviously it will give some reaction to this particular force. Okay, so these reactions are uniformly distributed over this area like this. Okay, in this cross section, the internal forces, so these are my internal forces, or I would say reactions, okay, to P, my applied load or applied force. So these reactions, if this is acting at the axis, or totally at the I can say along the axis of this particular bar, in this case, this distribution of internal forces, which is opposite in nature to the load or to the force, this will be uniform distribution. Okay, it can be of non-uniform distribution also if this force is not acting exactly along the axis of the bar, so it can be of non-uniform distribution. But now we are considering that it is acting at the axis of the bar, along the axis of the bar, and we are getting a uniform distribution of reaction forces over this cross-sectional area. Okay, over this cross-sectional area. So if we just sum of this all forces, all reactions, okay, so if I define it as, suppose R1 summation of R, I would say summation of R, so we will see that P should be equal to summation of R, because we know the action and the reaction will be opposite to each other, but there will be equal and opposite to each other, correct? So this uniformly distributed reactions over this area, okay, if we sum this all the reaction forces, we will see that it is equal to the force that we have applied, the point force that we have applied on the bar, correct? So this sum of reaction forces uniformly distributed along this cross-sectional area, if I just define this cross-sectional area as A, okay, I will write it as cross-sectional, I will write as cross-sectional area equal to A. So this cross-sectional area, if we define it by A, and if we sum all the reaction forces as sum of R, so this total number of forces spreaded over this area, okay, so this particular thing we call it as, we define it as sigma, one particular symbol which is sigma, and we call this as stress. Okay, we call this as stress. So whenever we will be applying some force on an object, if it is, whether it is along the axis or maybe with some eccentricity, there will be some uniform or non-uniform distribution of reaction forces at any section of the object. If we create a cross section, there will be any section of the object, you will see some uniform or non-uniform distribution of the forces. The total amount of force, reaction force, distributed over the cross-sectional area. Okay, so we will if we find it, how much you can say, what is the total amount of force per unit area. Okay, if this is we call it as, you can say load by, or I would say P by A. Summation of R is equal to P, right? So if we just uh, replace R by P, so I would say that the total force applied on a unit area, so we call it as stress, which is we denote it by sigma. Correct? Right? So we have applied load and stress happened. Now what we have seen, that due to the applied load, some elongation is also happening. Okay, some elongation is also happening. Now if I go back to the, you can say, Hooke's law. So Hooke's law says, Hooke's law, it says that change in length, which is the elongation, equal to applied force into total length of the bar. Okay, suppose this is the total length of the bar and this is the delta. Correct? So is equal to A into E. So now if you see, if I replace, this particular thing, uh, delta equal to P by A, we know we can write it as what? We can write it as am I doing any mistake or something? No, we can write it as sigma multiplied by L by E. Okay, we can write it as sigma multiplied by L by E. Correct? Okay, so now this thing, first thing we have done. Now let us do one more thing. What we will do, that we have applied some load, our total length was L and the change in length is sigma. So if we do the change in length over total length, how much change is happened in the total length? So this ratio we define it as another symbol, which is epsilon, and this particular thing we call it as strain. That due to the applied load, due to the applied force, whatever change in length happened over the total length. Okay, so change in length by total length, this ratio we define it as I can say epsilon, and we call it as strain. Okay, we call it as strain. So if I just now do it like this, sigma, I take L here, so I will say stress multiplied by 1 by Young's modulus E. Correct? Fine. So now this thing we can replace it by epsilon. So epsilon equal to sigma by E. Okay. So we have defined stress, which is which you already seen. What is strain? The change in length over the total length, it is the strain. So which we define it by you can say epsilon. We have replaced first stress. So this P by A we replaced by sigma, and this delta by L. So we have seen delta by L is nothing but the strain. Change in length by total length, it is nothing but strain. So we you can say replaced it by our epsilon. So we know these two definitions. These two definitions we know, but we need to find this E, which is my modulus of elasticity. So how can we define it now? How can we define it now? We can easily define it now. So if I want to find modulus of elasticity E, it will become stress by strain. So now what is the definition? What is the definition of modulus of elasticity? So we can say modulus of modulus of elasticity modulus of elasticity equal to stress by strain. So what do you understand by this? That due to an unit amount of stress, or no, it's I'm saying it reversely actually. Due to a unit amount of strain, that means change in length over the actual length. Okay, so due to the unit amount of strain, the amount of stress that will be inducing at unit area of the bar or of the object, that particular amount of unit stress due to the unit amount of strain is known as my modulus of elasticity. So obviously it will change, it will vary from material to material, because the amount of strain will be varying material to material. So as the strain is changing, obviously the stress will also be changing, because we have seen the strain and stress also. We have seen what strain equal to stress by E. So we can say strain is also proportional to stress, correct? Or stress is also proportional to strain, correct? So here what we have understood, that due to some unit amount of strain, or you can say due to some unit amount of change in length over the actual length, whatever stress is being induced in a unit area of the unit area, means suppose this the total area, so this is the unit area. So in this unit area, what is the total reaction force distributed? Okay, this is my stress, correct? So in this unit area, what amount of stress is induced? So that is known as the modulus of elasticity, which we denote by E. Okay, so I hope it is clear. I hope it is clear what is stress, what is strain, and what is modulus of elasticity. So that's why I have not defined it here, I have defined it here. Okay, once we understand stress, then we understand strain. So by relating the stress and strain, we'll be understanding the modulus of elasticity. Now, different materials will have different you can say values of this modulus of elasticity, that we will see later. So this class was to understand this fundamental of stress strain and how we have achieved it from the Hooke's law. So you can see how Hooke has defined this simple linear, you can say how he has formulated a simple formula, okay, which is giving us the definitions of stress, definition of the strain, definition of the Young's modulus, and also telling us about the behavior of the objects of different material. Okay, you change the E value, you can understand what is the, suppose you take some material, you put the E value for that material, you understand how it is behaving. Okay, so obviously what we understood, stress is proportional to strain. If you increase the strain, stress will be increasing, correct? And again we have understood how stress and strain is defining the modulus of elasticity of a material. So if you do not know the modulus of elasticity of a material, if you give an unit strain in an object or in a bar of a particular material, and you find out the stress for a unit area of this particular, of the cross section of the bar, you can easily find out the modulus of elasticity also. So obviously that is what the Mr. Hooke has done, or many of the scientists have done, and they have given us this simple, you can say, linear formula, which is this one, delta equal to PL by A. Okay, so I hope this is clear. I know I have made this very basic, And if I made any mistake in between, please do let me know so that I will correct in my next lecture. Okay, to let me know in the comment your opinions also, your suggestions also, to improvise the way I am explaining, because I have also read, I have also brushed up few things and then I am delivering it. So if I made any mistake, please pardon me and tell me where I should correct it. Or if you have any suggestion regarding the improvement of the content, I will, please do let me know. I will try to improve it, or try to apply your suggestions in the next lectures also. Thank you, and see you in the next lecture.